Hello, good afternoon all. So today we will study the Frank and Hertz experiment. Uh, During the last lecture, we have studied the two mechanisms by which the atomic excitation can occur. The first mechanism we have studied is the excitation by the collision with another particles, for example with electrons. So when such fast moving electrons are bombarded with the atoms, and if the energy carried by these electrons is sufficient for those atoms to put them to the excited state, then that energy carried by the electrons is absorbed by the atoms and the atom is excited to above the ground state. So that is how the excitation process can take place by the collision. And in the second process of atomic excitation, we are saying that if a certain photon is incident on the atom or the material, then if the energy carried by that photon is sufficient for that atom to put to the excited state, then that photon will be absorbed by that atom and the atom can be put to the excited state from the ground state. And as we know well that these atoms cannot remain in the excited state permanently, but the maximum time up to which these atoms can remain in the excited state is of the order of 10 raised to minus 8 seconds. So immediately thereafter, those atoms return back to the ground state, and during the transition from the excited state to the ground state, these atoms radiate certain amount of energy in the form of photon of energy h. And this energy h is found to depend on what is the energy difference between the two states, the ground state and excited state. So that the frequency of these radiations will be different, and as the frequency is different, the wavelengths of the radiations also will be different. So that is how we get the spectrum. Now, in 1914, it was the Frank and Hertz who performed a series of experiments based on the excitation by collision. These experiments demonstrates very well that the atomic levels does exist in the atoms, or these energy states of the atoms are discrete one, and these atomic levels are found to match well with those observed with the help of the spectrum, light spectrum. So the apparatus used by Frank and Hertz to study this atomic excitation consists of an evaporated glass tube, almost evaporated glass tube. Near the two ends of this glass tube, near one end a cathode, or we can call it as the filament, is placed. Between the two ends of this filament, a low tension battery is connected, preferably DC source, so that a constant current can flow through this filament, and due to this constant current flowing through the filament, the temperature of the filament increases, and due to the increase in temperature of the filament, the electrons, or we can call them as fermions, are emitted from this filament, and those electrons that are emitted from the filament are accelerated towards the plate fixed at the other end of this glass tube. The atoms of the material under study in the vapor state are filled in this glass tube at a very low pressure. At a very low pressure, the vapors of the material, atoms of the material under study are filled in this glass tube at very low pressure. So these are the atoms of the material under study, and these atoms are existing in the vapor state in this last degree. There is a grid in between the filament and the plate. A large or high potential difference or variable potential difference we can consider it to be applied between the filament and grid, so that the filament is given the negative potential and the grid is given positive potential, so that the electrons emitted from the filament are repelled by the negative potential and they are attracted towards the grid, which is given the positive potential. So these electrons are accelerated towards the grid or towards the plate, rather we can say, because as these electrons approach to the grid, and since this grid is perforated, some of the electrons may pass through the holes to the grid and they can reach to the plate. But there is a certain small negative potential is applied to the plate with respect to the grid, and this potential is called as the retarding potential. This potential is called as retarding potential. Why this negative potential is applied to the plate with respect to the grid, that we will see later. Now let us see what happens as we increase the potential difference across filament and grid. So if the potential difference applied across filament and grid is increased gradually, what will happen is that those electrons that are emitted from the filament will be accelerated with greater and greater velocity, greater and greater kinetic energy, so that more and more number of electrons can reach to the plate, and when those electrons reach to the plate, they will be circulated in the external circuit, and when these electrons are circulated in the external circuit, they will constitute a current to flow in the plate circuit, so that this ammeter connected in the plate circuit will show certain current or deflection. Now, if we plot the variation of the current flowing through this plate circuit with the potential difference applied across filament and grid, how this current varies, let us see. If we plot the variation of the plate current with respect to the accelerating potential field, this graph is of this type. So if there is the voltage of 2 volt, 4 volt, 6 volt, 8 volts, 10 volts, 12 volts, 14 volt, 16 volt, and so on. And we have the current on y-axis. So these are the lines of voltages: 2, 4, 6, 8, 10, 12, 14, 16, etc. Now, the current is plotted on y-axis like this, maybe 2 milliampere, 4 milliampere, 6 milliampere, 8 milliamperes, and so on. So initially, as the accelerating potential field is increased, the positive potential given to the grid with respect to the filament is increased, the plate current is found to go on increasing linearly, not linearly, varies, increases with the increasing potential, and it is found to attain the maximum value at a potential of about 4.9. So this current increases, and when the accelerating potential becomes equal to 4.9 volt, the plate current abruptly decreases. The plate current abruptly decreases to a very low value. Thereafter, again if we increase the potential given to the grid, positive potential given to the grid with respect to the filament, the plate current further increases and attains a second peak at about 9.8 volt, and further if we increase the accelerating potential, further the current decreases and once again it approaches to a maximum value at about 14 volts and so on. So this is the nature of the variation of the plate current with respect to the accelerating potential applied across filament and grid. Now the question arises, if we continuously increase the potential difference applied across grid and filament, the plate current should continuously go on increasing. But what we observe here in the graph is that we observe the sharp drops in the plate current at certain fixed potentials. We observe sharp drops in the plate current at certain fixed potentials. Now the question arises, why do we observe these drops in the plate current? Now, the explanation for this is like this. When the accelerating potential corresponds to this particular value, when the accelerating potential corresponds to this particular value, peak value here, the energy carried by these electrons is such that when these moving electrons collide with the atoms of this material in the vapor state, the energy carried is sufficient for those atoms to put them to the first excited state. So when almost all the electrons collide with the different atoms of the material in the vapor state in this tube, number of electrons reaching to the plate decreases, and if the number of electrons reaching to the plate is decreased, the plate current falls or abruptly decreases. Now, why only at this particular potential, accelerating potential, the current decreases? The reason is that at this particular accelerating potential, the kinetic energy carried by the electrons is sufficient for those atoms to put them to the first excited state, and when these electrons collide with the atoms, the collisions are inelastic. The collisions are inelastic, and because of this inelastic collisions, what happens is that almost all the energy carried by the electrons is absorbed by the atoms in the vapor state, so that these electrons then moves with very low velocity. They have to accelerate themselves due to the accelerating potential, and hence the number of electrons reaching to the plate per second drops at this particular potential, and that is why the plate current decreases. Once again, when the applied potential or accelerating potential applied between grid and filament is further increased, then the kinetic energy carried by the electrons is greater than the energy required for those atoms to put them to the first excited state, and is less than the required for these atoms to put them to the second excited state, so that more number of electrons reach to the plate, and hence the plate current further go on increasing and attains a maximum value at this particular accelerating potential, where it once again decreases, because at this accelerating potential the kinetic energy carried by the electrons is sufficient for those atoms of the material in the vapor state to put them to the second excited excited state, and once again the collisions are inelastic. Whatever the kinetic energy is carried by the electrons, all that energy is absorbed by the atoms, and the atoms are put to the second excited state, and hence the number of electrons reaching to the plate once again decreases, and hence we observe the second drop in the plate current. Once again, if the accelerating potential is further increased, once again the number of electrons reaching to the plate further go on increasing, so that the plate current once again increases, rises, and attains a certain peak value at a third particular accelerating potential, where the energy carried by the electrons is sufficient for these atoms to put them to the third excited state, and hence at this particular accelerating potential once again we observe the drop in the plate current. So this nature of the plate current, variation in the plate current, clearly indicates that these atoms does possess the discrete energy states. This nature of the plate current, variation in the plate current with the accelerating potential, clearly indicates that the atoms of these materials does have the discrete energy states, and those energy states corresponds to the accelerating potential. Here is of the order of 4.9 volt. First drop in the plate current is observed at 4.9 volt. The second drop in the plate current is observed at a potential of about 9.8 volt, which is multiple of first drop. Then the third one is observed at 14 point something, 14 point till then 14.7. So here it is observed at 14.7 volt, and so on. So all these drops in the plate current are found to be the multiples of the first drop. So this clearly indicates that the atoms does possess the discrete energy states, and this can be verified by calculating the energy of a photon emitted by these atoms when the excited atoms return back from the excited state to the ground state. They will emit a radiation of certain frequency, of certain wavelength, and by measuring the wavelength of these radiations, or by measuring the frequency of these radiations, we can calculate the energy carried by those photons. So for the sake of understanding or simplicity, if we consider the fall in the plate current observed for a voltage of 4.9 electron volt, and if we observe the spectrum of the line at this particular accelerating potential, the wavelength of the radiation is found to correspond to 253.6 nanometer. The wavelength of the radiation corresponds to 253.6 nanometers. Now we can calculate the energy carried by this photon, whose wavelength is 253.6 nanometer. Now the energy of a photon E is given by E equal to h into nu, and as we know the relationship between the frequency, velocity and wavelength as phi is equal to n lambda, or u into lambda, where we c, we can use the expression, the symbol for velocity of light as c. So c is equal to nu lambda. So we get the expression for nu to be equal to C upon lambda. So using this expression for nu here, we can express this as Hc upon lambda. So the energy carried by this photon is equal to Hc upon lambda, where h is Planck's constant, c is the velocity of light, and lambda is the wavelength of the radiation. So substituting the values of these constants here, we get the energy of this photon E is equal to h. The value of h is 6.63 into 10 raised to minus 34. 6.63 into 10 raised to minus 34 into c is 3 into 10 raised to 8 divided by lambda is 253.6 into 10 raised to minus 9 meter, because this wavelength is given in nanometer, so it is 10 raised to minus 9 meter. If it was expressed in angstrom, then it would have been 10 raised to minus 10 meter. So if we evaluate this factor works out to be equal to 7.84 into 10 raised to minus 17 joule. This factor works out to be equal to 7.84 into 10 raised to minus 17 joule. And if we express this energy in electron volt, we have to divide this factor by 1.6 into 10 raised to minus 19. So by dividing this factor by 1.6 into 10 raised to minus 19, the energy in electron volt works out to be equal to 4.9 electron volt. So the energy carried by this incident electron is equal to 4.9 electron volt, and this corresponds to the energy of the photon emitted by this excited atom when it is excited from the ground state to the first excited state, and when that excited atom returns back from the excited state to the ground state, it emits a photon of energy 4.9 electron volt. So this energy of the photon emitted during the transition of the atom from the excited state to the ground state is equivalent to the energy carried by the incident electron. Energy carried by the incident electron when is accelerated from the filament towards the grid, and that gives rise to the equivalence, or the energy carried by the incident electron and the energy of the photon emitted matches well, which clearly indicates that the atoms possesses the discrete energy states. These atoms possesses the discrete energy states. Now, the question then arises, why this plate is given the negative potential with respect to the grid. The plate here is given the small negative potential called as a retarding potential with respect to the grid. This is because if some of the electrons have very less kinetic energy, those electrons also can reach to the plate, constituting a very small plate current to flow in the plate circuit. So in order to restrict the electrons with very low kinetic energies from reaching to the plate is given a small negative potential with respect to the plate, and those electrons with very small kinetic energy are restricted from reaching to the plate, and for that purpose this retarding potential is applied. So that is how we can conclude, or from this Frank and Hertz experiment, we can conclude that the atoms does possess the discrete energy states. Atoms does possess discrete energy states. And with that, we come to the end of this fourth chapter on atomic structures. Okay.